Let's look at geometric sequences series. We're going to do these four things. We're going to write the equation for the nth term and apply it. We're going to find a series, which is the sum. We're going to do an application, and we're also going to look at sigma notation or summation notation. Let's start off with writing the equation that we need. The basic general equation or format is this, where we have the first term, or, well, actually the amount at the nth term is equal to the first term times the ratio, and then the term number minus 1. All right, so a term amount is equal to the first term times the ratio raised to the power of 1 less than the number of the term. That's our n minus 1. So the two things that we need are A1 and R. So the way we find R in something like this is to find what the ratio is between each set of numbers. What we do is take the second one, I meant to put 2 there, let's put a 2 now. Take the second term amount and divide it by the first term amount. That's 4 over 2, that equals 2. Now let's do it with the third term divided by the second term. That's 8 over 4, and that's also equal to 2. So that means from here to here, we multiplied by 2, then we multiplied by 2. Let's see if that holds true here and here. And yes, it does. That means that R is equal to 2. Now that we found R, now what we're going to do is take the equation and put in the two things that we need, n minus 1. We don't know the amount right now, or we don't know the term. This is set up, the general equation is set up so that you can then decide after you have it what term you want. So right now, we're going to put in these two things we know, which is the amount of the first term, and then the ratio, and then the n minus 1. So that is our equation. If I wanted to know something like the 11th term, so let's move down to here, I would take that equation and say the amount at the 11th term is equal to the first term times the ratio, and then 11 minus 1. So here we have the amount, the 11th term is 2 to the 10th power. The amount of the 11th term is 2 to the 10th power is 1024, which equals to 2048. And that's the amount of the 11th term. So here we have the general term for this particular sequence. And here we've used it to find the amount at a certain number, in this case, the amount of the 11th term. Okay, now let's do with another one where there's negative signs. And here there's going to be the same process, just a little bit of different result. So here I'm going to need to figure out what to do to get from here to here. So let's do A2 over A1, negative 4 over 2, that's a negative 2. Then we're going to take these two, A3 divided by A2 is 8 over negative 4, same thing, still negative 2. I'll do it with the next two. A4 over A3 gives me negative 16 over 8. Okay, now it's getting redundant, but for a reason. So if I multiply this one by negative 2, I do indeed get the 32. So now we know what R is. R equals negative 2. The amount of the first term is a 2. So let's repeat the same basic thing here of the amount at the AN right now is equal to A1 R n minus 1. So the general form would have a 2, a negative 2, and then n minus 1. Okay, let's find what it is at, say, the 10th term here. So that's, well, first I'm going to do this because that is making the equation. I'm going to yellow it in. Well, let's go one step further and say for the amount of the 10th term, 2, negative 2, 10 minus 1. The amount of the 10th term is 2, negative 2 to the 9th power. Okay. Now, don't let the negative, the 9 throw you, because all you have to do is think, 2 times 2 times 2, and, this one's an easy one. 2 squared is 4, so let's do the first power, second power, third power, fourth power, fifth power, sixth power, seventh power, eighth power, 256, and then the 9th is going to be, what's that, 500, okay, 12, yeah, 512. Okay, let me make that so it's clearer to see. You can do this relatively easy with 3s and the 4s if you want to work it out carefully, but you then can also use the calculator to put the number in. Well, now that I've got this, what we also have to think is that this one was negative 2 times negative 2, so that one was a positive. This one then, oh no, that's negative 2 to the first, my mistake. So 2 to the first would be, here in this case, it was negative 2 to the first, so we keep it as a negative 2. Here it was negative 2 times negative 2, so it's a positive 4. Now it's 3 negatives, so it's a negative 8. 4, the negative cancels out. This one, the negative comes back in. So look at that one will be a negative, positive, negative, positive, negative, positive, negative, positive, negative. So all of the odd exponent terms for working this out are going to be negative numbers. So the amount of the 10th is 2 times negative 512. And therefore the amount of the 10th to the 10th power is negative 1024. So that's how you use it with a negative. Just be careful with the negatives, put in the calculator correctly, and this will give you the negative 512. Just be careful using the negative on the calculator. You can't use the minus sign, you have to use the plus minus key, which changes the sign as opposed to subtracting. All right, now let's take a look here at the sum of the first 5 terms of the sequence. Now, what we're going to be doing is adding these up because that's what a sum does. Okay, that makes this a series. And there are 2 ways you can do it. One of them is just to add them. The other way is to use a formula. With these easy ones, it's relatively easy right now to go ahead and just think like add them together because we've got 6 and 8, that's 14 for all these. 16 and 14 makes a 30 and a 32. It looks like it's 62. Okay. And I can get that just by adding up the totals of them. 1, 2, 3, 4, 5. We also can do it using a formula like this. So what we need for the formula, the sum out to a certain number of terms is the first term times 1 minus the radius and then the number of the terms. And on the bottom, it's 1 minus r. So this is an easy one to use here with this 5. We already know the answer should be this. Let's go ahead and work it out. So the sum for the first 5 terms is the first term, 1 minus the ratio here is times 2 every time. So the ratio is 2, and it's to the 5th power. Notice it's not n minus 1 like it is in the general form. So you have to think about the difference between this form and that form, both purpose and the fact that it's n, not n minus 1. 1 minus 2. All right, so we work this out. Sum of the to the 5th is 2. Well, 2 to the 5th is 32. 1 take away 32 is a negative 31. And then 1 take away 2 is -1. So we get a -62 divided by a -1, and that means we get a 62 just like that. So if it's easier and you're not required to use the form, then you can add them up. But in some cases, the form will be better if there's a much larger amount of terms, or if you're dealing with a negative, I think it'll be fun to do this one. Okay, let's do this. Okay. The formula, okay, well now it's the same format, same sequence, except for the negatives here. So we have the -4 and we have the -16. That means just like from the first page, our R is -2 and A1 is 2. So we can still use this. The sum for the first 5 terms, because there's 5 here, so we'll count that for that, is going to be the first term, 1 minus -2 raised to the 5th power, and then 1 minus the -2. So here, I'll continue first here before I come back down. 1 minus, well, -2, -2, -2, 5 times means it's going to be a -32 result. Oh, and this, of course, becomes plus. 1 plus 2 is a 3 on the bottom. Well, this also becomes a plus. So now the sum to the 5th is equal to 2 times 1 plus 32 is 33 divided by 3. Well, 3 goes into 33 11 times. 2 times 11. So, or you can do it as 66 over 3 and reduce that way. You're still going to get a 22 regardless. Okay. So it's a different and smaller number than the one above, because each time that you add some, the next time you subtract some, and you actually subtract more. So if we did the next number after 32, if we did -64, well, that would make this a much smaller number, or a negative number for the sum up to that 6th term. Then when we do the 7th term, it would go back to being a larger positive. And each time it's going to switch back and forth. Okay, let's take a look at an application problem involving geometric sequences. Okay. So population of a city rises on average 6%. The population is this much in 2021. Okay, and so if that is the beginning year, then we're going to go to 2026. Now, this is going to be an exercise in thinking about including the years too. Because what I'm going to do, I'm going to do this through 2 methods. Method 1, let's do 2021, and that's the first year. You could call it the 0th year and not count it until the next one. Well, I'm going to think of it as the first year here. Okay, and do it as, let's see, because that's the first number, almost like this is A1. Think of it as the amount at the first term. So this is our first term. That's, you haven't usually thought of that when you're counting things or listing things, but it really is. The first one's the first term, and then the second term, and so on. So the first term is 70,000. Then in 2022, the second term, you're going to multiply this, and this is an important little thing. If you're going to go from this to the next number, the average of 6%, well, we don't multiply by percents. You have to change that into a decimal, 0.06, and multiply by that. Multiply 0 by 0.06, and then what you get is 74,200. Better of a comma there. Now in 2023, the third term, again, multiply by 0.06, but now we have a slightly larger number, so we're going to get a little more out of it. This is also called compounding when you deal with it with financial things as well. It's compounding interest, because new interest that's put in is compounded. The new amount of people that go in, then you're going to get more people later in the city. 2024, multiply this number by 0.006, and I'm going to get 83371. Now, the interesting thing here is you can't have a partial person. I'm going to wait until the end to round that, though. So let's go ahead and multiply them all out, because you see that to get to 2026, this is now 6 terms because of the original one being the first term in this concept and context as a series. So now we have 88,373.387 and so on. Well, I'm going to multiply that one and get to 93,675.79. And now at this point, this is where I'm going to cross out the decimal part. And I wanted to actually wait till now because this part here, normally you would round the 5 to a 6. But since you're talking people, there's no partial people. So you basically round down every time when in this context. So although 93,675 people is rounded incorrectly based on normal rounding rules, it would have been a 6 here. For practicality and being reasonable, it doesn't make sense to round it to 6 because you don't have a partial person. So that is our answer for that one. There's another method, of course. We can use the formula. Now I'll do the black one here. The amount at a term is equal to the amount of the first term times the ratio to the n-1 power. So the amount of the sixth term is equal to the amount of the first term, which is 70,000, times the ratio, which is the 1.06. Oh, I need to go back and fix something in concept here. And then we're going to have 6 minus 1. I put 0.06 because that's what 6% is, but I forgot to mention, and I'm going to have to therefore change this, that in reality, when you multiply by 0.06, you would only get the 4,200, and you would have to add it to the 70,000. So 0.06 is not necessarily wrong. It just means 2 steps. You have to get 4,200 and then add it. And then this next one, you get 8652 and then add it to 70,000. Well, instead, if you multiply by 1.06, the 1 includes the 70,000, and then the 0.06 is now the extra people. And on this one, multiplying by 1.06, you include the 74,200, and then the 0.06 gives you the extra to give this number. So it's actually 1.06 that makes more sense to multiply by. And that's why it has to be used over here. It's the ratio plus 1. And that's what the actual ratio is, because that's the amount that you would multiply each number by to get to the new number, not just the extra number of people, but rather to the complete full population. Now, having said that, let's actually calculate out. First, this is going to be to the 5th power. And then at that point, you just put this into the calculator, but make sure you're careful to do order of operations. You do that first, and then you do that second. And when you do get that, you get the amount of the sixth, the amount of the 6th term, or in this case, the 6th year, is 93,675. Like there's rounding in there, but on the calculator. But again, you don't. Whoops. I also thought of something else. What I have to do here is say it's that many people, because saying A6 wouldn't be part of the answer, because A6 is a construct that I just made up. Well, because it's a normal thing to do in this kind of context. But it's not, it doesn't have anything to do with the people. You actually have to say this is people. It's like using the right units. So I'll say that over here too. People. All right, so that's 2 ways to do it. This way works great if you only have a few numbers to deal with. This one's much better if you're out to like the 10th or 15th term, especially if with a ratio where you're getting lots of decimals and lot more larger numbers or really tiny numbers. All right, now let's take a look at sigma notation in this context for geometric series. And this is the sum formula to use for geometric sequences. There are others as well, but this one will cover everything that we're doing in this section. So when I look at this, I look to see if this part here is in the format of A1R n minus 1. It is indeed in that format. That means this is A1, and it means that this is R. We also see that we're going from the first to the fifth term. And even if you count the ones, so it's 1, 2, 3, 4, 5, so that means that n is equal to 5. So what we're going to do, well, actually, let's take a look over here and see if we have everything that we need. Okay. So for the sum, I need the first term, I need the ratio twice, and I need the number of terms. I have all those things. Now I can do it the long, hard way of multiplying each one of them in, or I can actually do this sum formula. I'm going to do both. I'm going to use the sum formula first, so the sum to the first 5 terms is equal to the amount of the first term, which is 2, right? 1 minus the ratio, which is 2, raised to the nth power, okay, not minus 1 here, just the, but here it's the 5, so raised to the nth power is 5, and on the bottom, 1 minus 2. So the sum of the fifth is 2, 1 minus 32. Ooh, I think we've seen this before, but that's okay. We get negative 31, we get negative 62, we get a positive 62 answer. The other thing I could do is find the amount of the first term, okay, which is, remember, it's A1 times R times n minus 1. Well, of course, we know it's the 2 already, but if I were to do this formula, I would do this. 1 minus 1 is 2, 2 to the 0, and anything to the 0 is 1, so that means 2 is the amount of the first term. For the second term, 2 to the 2 minus 1, which is 2 to the first, which is 4. Amount of the third term, 2 to the 3 minus 1, and now we have 4 times 2, we've got 8. And now you pretty much know what the other ones are because we're doing the same thing. So because we knew all of these weren't hard numbers to see, but if you add them all up, they all equal to 62 also. You are going to want to use the sum formula when you have any larger amount of numbers, or if you just don't feel like doing all this extra work here. Here is one where it doesn't make sense to start doing from the 5th term to the 23rd. You have like 18 terms to do, or 19 terms, or 20 terms. Well, that's going to be something to indicate here. Okay, so let's see what we can figure out. This is A1. This is the R. And we are not going from the 1st term to the 23rd term. What we have is the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20th, 21st, 22nd, 23rd. Aha. So from the 1st to the 23rd, that would be 23 terms. But I'm taking away 4 of them. I'm going from the 5th term to the 23rd. So it's 23 take away 4. That's going to be 19 terms, and it'll be 19. This is not the way you have to do it, but it's one way to recognize that it's not as simple as 23 minus 5. I get 5 on my head too much. It's not as simple as 23 minus 5. okay if 23 minus 5 and then add 1. And the reason for that is because it is inclusive. When you do 23 take away 5, you're not including the 5th term. Okay, you're going from the 5th term, but not including it up to the 23rd. That's only 18. 23 minus 5 is 18. But if you hand count all these, you're going to see that there are 19 of them. And that's because usually if you start at number 5 and you start counting, then you go 1, 2, that'll be 1, that'll be 2, 3, 4, 5, 6. So you didn't include the 5. Well, here you do want to include the 5. So 23 take away 5 would be equal to 19, it's 18 rather. And then, but when you add the 1 to include both ends, now you're at 19. That's an important distinction because it's not something people recognize easily. Most people simply do this, but they don't want to, or they should not want to do it, I guess you could say. What this means, though, is that now we know that the n is 19, and for the formula that we have, it's the sum at the amount of the term, or the sum up to that number of terms, is equal to, and that's going to be interesting to write about in a second, to mention it, is going to be the amount of the first term, 1 minus r to the n, and divided by 1 minus r. Okay, let me check something back on these formulas here. You know, that's right there. So this is from, I could say 19, but that could be misleading. It's not the sum of the first 19 terms. So this actually is not important, not very important. You can just leave it Sn. In my case, I'm going to call it S5 to 18. I'll put an arrow. 5 going to, oh, not 18, 23. 5 to 23. And then that makes sense. I think I need to write that so it's a little easier to say. So 5 to 23, and that's equal to the first term, which is -6, and then the ratio, or 1 minus the ratio, -3, the number of terms, which is 19, and here's where you see it's really important. If this was 18, that negative here would cancel out. With 19, it being an odd number of times it's multiplied to itself, that negative will stay. And underneath it's 1 minus a -3. So we are going to get -6, 1 minus negative 1,162,261,000,000. Oh, 1,162,261,467, and all that, divided by 1 plus 3 is 4. And then this is going to be adding it, so we're going to get one number slightly larger. So 1 plus that will make that 7 into an 8. Then we're going to multiply by -6 and plus, then that should give us -1,743. Oh, not 7. So, and we're dividing by the 4. Let me write this all out. Okay, so we get 1,743,392. Was it? No, that's million. This is million and this is billion. I have to go this way to make myself right on it. 1,743,392 million. Oh, that's billion, million, thousand. So 1,743,392,201, and it's negative. I deal with some larger numbers, but not so much all the time. I have to stop myself to make sure I say these correctly. Last thing here is an infinite series. And the infinite series occurs when the ratio is less than 1. If you go back to all these examples, but here's the thing, when the absolute value of it is less than 1. Here we have a -3, the absolute value of that 3 is positive, therefore it's not infinite. There's an actual, if you kept going, you've got a, you can have a sum for that. Same thing on all these. I think I have all of them with, now this one, because the ratio is 0.06. Well, actually, let's come back here and do this one. There's an infinite geometric series. And so if you have this instance, then it is an infinite geometric series. And here's the sum formula for the sum out to forever. Now, that's the interesting thing. How can you have a sum where you keep adding numbers and they never stop? The reason that you can do that is because a ratio that's both between 0 and 1 is going to make it smaller every time. So look at this example. We have 16 going to 12, going to 9, 6.75, 5.062. After hundreds of numbers, you're going to get at 0.00000001, and then 0.00000001, that's one more. So it's going to get down where it's so small, it's close to like 0 at the end. And mathematicians have said that the end of that, because when you go out really, really far, you're essentially dealing with 0. That means all the other numbers can be added up to a certain number. And this is how we figure it out. So the infinite sum is equal to the first number, the amount of the first term, divided by 1 minus the ratio. Well, the ratio is A2 over A1, which is 12 over 16. 12 over 16 is 0.75. A3 over A2 is 9 over 12. That's also 0.75. And if you use your calculator to multiply each time, 9 times 0.75, you get this. Then 6.75 times 0.75, you get this. So it works as what R is. So that's going to be R. And that means we're going to subtract 0.75. So the infinite series sum is 16 over 0.25. And when you divide that, you get 64. You can also think of that as 1/4 and then multiply by the reciprocal, 16 times 4, and you're going to get 64. So you want to know this formula as well for infinite series, and it's actually very simple. You only need to know the first term and the ratio, because the number of terms doesn't matter. It's going to go out forever and forever, and at some point it's so small or tiny that it's almost like adding 0 each time. And 64 is what you get before you get to that point. I hope this helped with this section. Thank you for listening.